You know that feeling, right? You step into an elevator, the doors slide shut, there's that low hum, and you just go up. It feels so smooth, so automatic. But what you don't realize is that behind that calm, quiet ride, there's a constant battle happening against this powerful, totally unseen force. And if that force wins, well, that's when things can go very, very wrong. So what is this hidden force? And how are engineers fighting a battle we never even see?
So, what do you think it is, the single most critical point of failure? I can tell you, it's almost definitely not what you're thinking. It's not the main motor burning out or a power failure. Nope. The most dangerous threat is something incredibly small, a tiny, tiny deviation that can silently tear the whole system apart from the inside out. So, in this explainer, we're going to pull back the curtain on this hidden challenge. First, we'll define this unseen danger. Then, we'll look at the anatomy of a failure, how one little thing cascades into a huge problem. After that, we'll see how the pros diagnose it, and finally, we'll check out the blueprint for making sure everything stays perfectly safe.
Okay, let's get right into it. We need to put a name to this invisible enemy. It's something called wire rope deflection.
The best way to think about it is like the wheel alignment on your car. You know, if it's off by just a tiny fraction of an inch, you get weird vibrations, your tires wear out unevenly, it's a mess. It's the exact same idea here. Those big steel ropes in an elevator, they are supposed to run in a perfectly straight line over their pulleys. Any little deviation from that path, and I mean, we are talking about millimeters, and you start introducing some serious stress into the whole system.
Now, here's the thing. This deflection isn't just one problem, it actually comes in a few different flavors. First up, you've got radial deflection. This is basically an up and down shift, where the rope is sitting either a little too high or a little too low in the groove of the pulley. This creates all this uneven pressure and a very specific kind of wear and tear.
Then there's axial deflection. And according to the analysis from experts at Novin Puya Lift, this is hands down the most common and the most destructive type. This is a side-to-side drift. The rope is constantly rubbing against the inside walls of the pulley groove, and that friction? It's like taking sandpaper to hurt the rope and the pulley, just grinding them away over time.
And last, we have angular deflection. Engineers have a cooler name for it: fleet angle. This happens when the rope doesn't enter the pulley perfectly straight on, but at a slight angle. It might not look like much, but it actually forces the rope to twist every time it settles into the groove. That little twist causes wear on the edges and slowly weakens the rope's entire internal structure. Now, I should say, not every single tiny deviation means disaster is imminent. I mean, global safety standards like EN 81 and ASMEA 17.1, they actually allow for a teeny tiny amount of what they call permissible deflection. But the real danger, the red zone, is when you cross that line into impermissible deflection, because that's the moment the clock really starts ticking towards a major failure.
So the big question is, how does an error that's almost microscopic blow up into a threat for the entire system? Well, it all comes down to a really destructive domino effect where one tiny problem just triggers the next, and the next, and the next. And the number one cause, by a long shot, is misalignment. It usually starts with an almost unnoticeable error during installation. Maybe the motor base is off by a hair's width or the guide rails aren't perfectly parallel. But other things can add to it too, like tiny imperfections in the parts themselves, or even just the everyday forces of the elevator starting and stopping over and over. And here is how that chain reaction really plays out. It all starts with that tiny misalignment that causes the rope to wear down unevenly, fraying on one side. Then, that damaged rope starts to carve into the pulley groove itself, changing its shape. This creates all these abnormal forces that put a ton of stress on the pulley's internal bearings, damaging them. And the final domino to fall? A massively increased risk of the rope slipping, or, in the absolute worst-case scenario, derailing from the pulley completely. And listen, to really drive home just how serious this is, a quote from that Novin Puya Lift analysis really puts it perfectly. The consequences aren't just about a single part breaking. They are, and I'm quoting here, extensive and destructive. This impacts everything from how smooth the ride feels, all the way up to the structural integrity of the entire system. It's a huge deal. Okay, so we've established the problem is really serious, and it's basically invisible. So how on earth do you even find it? Well, this is where the detective work begins. And it's this really cool blend of old school experience and seriously cutting-edge technology. So the first line of defense is just the trained senses of a really experienced technician.
They're looking for these super subtle visual clues, like maybe a shiny spot on one side of the rope that shouldn't be there. They're listening for sounds that are out of place, a faint scrape, a little creak, a ticking noise. They can even feel for unusual vibrations just by standing on the floor of the elevator car. These are the very first whispers that something bigger is wrong. But to actually confirm those gut feelings, you need tools, precision tools. Back in the day, that meant using things like calipers to measure the ropes and spirit levels to check if things were straight. Today, though, the toolkit is way more advanced. We're talking laser alignment systems, vibration analysis sensors, even thermographic cameras that can actually see the heat caused by friction.
And the jump in technology here is it's mind-blowing. We are talking about getting a precision of 1,000th of a millimeter. To put that in perspective for you, a single human hair is about 70 times thicker than that. That is a level of accuracy that is literally invisible to the naked eye, and that's what it takes to find and fix these hidden problems before they become truly dangerous.
So, okay, finding the problem is one thing, but preventing it from ever happening in the first place, that's the real endgame. And that requires a complete strategy, one that starts way, way before anyone ever presses the up button. And this brings us to what the experts at Noven Puya Lift call the blueprint for safety. It's built on 4 essential pillars. It all starts with the design phase, making sure the foundation is rock solid and all the angles are perfect from the get-go. Then comes the installation, where using laser alignment for that micron-level precision is an absolute must. Then you have the components themselves, only choosing top-quality parts from trusted brands like SKF or FAG that have the tiniest imperfections. And finally, there's ongoing maintenance, regular checks, measurements, and preventative fixes to catch any tiny changes over time. You see, real safety isn't a one-and-done thing. It's a continuous, comprehensive process. So the next time you're in an elevator, just take a second and think about the incredible amount of engineering and precision that's silently working to keep you safe. The forces are enormous, and the systems that control them are almost entirely hidden from view, which really leaves you with one final thought, doesn't it? If the system itself is this invisible and this complex, shouldn't the experts in charge of it be truly exceptional?